I need to make this perfectly clear. As we walk through this process, this is not something you're going to have to repeat. You need to know how to complete the square. I'm showing you how to complete the square. But this proof that I'm about to do is not something that you're going to see on a test. All right? I have a specific reason I'm doing this. Now, over a long period of time, I watched kids not do so well at completing the square based upon the method that Algebra 2 teachers were using. The method that they like to use is they take this leading coefficient right here and they factor it out. Can you give me another word for the word factor? Starts with a D. Divide, thank you very much. It's one of the mathematical operations that we do. Factoring is just dividing, breaking things up into two things that multiply back together to give you the original. So they like to factor out the A. And after they factor out the A, then what they like to do is take whatever's remaining here, the linear term, and they take this value and they cut it in half and then they square it. And they put it inside here. Of course, since they factored out an A, they got a set of parentheses, right? And then they put it in there. And then they have to ask themselves this question. How much did you really add to that side? Because guess what? Year after year after year, I watched kids screw that up. And then they would go to the other side and they would add the wrong number, and the problem was over. Because they didn't add the correct value to both sides. You have been programmed from a young age that whatever you add to one side of an equation, you also add to the other. True? You should have been programmed with that. So, in the way that the Algebra 2 teachers were doing it by factoring out that leading coefficient, they were disguising what they were adding. And kids would always screw up what they were adding to both sides. So I said to myself, why don't I just go back to the original and work out the algebra and figure out what number would I add to both sides and then do the factoring afterwards. So that's what I'm about to show you. You can see that I have added a fraction in blue. But obviously, the first thing I did here was I took C and I moved it to the other side, right? You see the negative C there on the other side. And then I added this fraction, b squared over 4a. Now that's a magical fraction that you're going to need to know, okay? Because that's going to help you in the future. So now I'm going to do the factoring out the a part after I've done that. Now, if factoring is another word for division, then what we're about to do is to go through here and divide each one of these by a. And if we divide that by a, what do we get? X squared. And if we divide that one by a, we get b over a times x. Now, division by a is the same thing as multiplication by what? We taught you that a long time ago in junior high, too. The reciprocal. So the reciprocal of a is 1 over a. So instead of writing a complex fraction here on this last one, I'm just going to write times 1 over a. Now, what is b squared times 1 in the numerator? That's just b squared, right? And then what about the denominator? 4a squared. Good. Now, might I remind you how to factor? For instance, what we have right here is called a perfect square. Now, you don't realize it's a perfect square because it looks nasty. But it's no different than a couple of these. So kind of remind me, how do you factor x squared plus 10x plus 25? That's a perfect square too. What is it the perfect square of? X plus 5. It would be x plus 5 times x plus 5. But in order to save ourselves some space, we just say x plus 5 quantity squared because we know that you're multiplying it times itself. How about x squared plus 6x plus 9?
What does that factor into? X plus 3, quantity squared. If you're at a party, you would want to say quantity squared. Otherwise, you get made fun of. Okay? What is the relationship between the linear coefficient and that number right there? It is half. Excellent observation. I like it. All right, so let's see if we can use that. Well, I'll do the first part. It's the heavy lifting, right? X. You knew that, though, right? It's the next part that I'm worried about. What are you going to do with that thing? If you said the logic was to cut it in half, division by 2 is the same as multiplication by what? 1/2. That would be b over 2a. b over 2a. That's cutting it in half. Now, this has a denominator of 1 right there, that negative c on the other side. Let's just remind ourselves, what would we need to, if we needed to get common denominators, like what is this denominator missing? It's missing a 4 and an a, so I have to multiply the top by 4 and a to get common denominators, and then I can add those two things together. And if I add them together, I'd have what? Negative 4ac plus b squared all over 4a. Now, you're not recognizing that numerator, more than likely, so let me switch it. Okie dokie. What are we going to do to both sides to get rid of this a right here? What are we going to do to both sides to get rid of that a? We're going to divide by a. Now, division by a is the same thing as multiplication by 1 over a. So I'm going to multiply, and I think I need to scoot that over a little bit, by 1 over a. Put a little equal sign in there. Of course, that really was the same thing as this, so to be technically accurate, I'd have to put it in there. Anyway, so of course it gets rid of that right there, giving us x plus b over 2a, quantity squared, equals, what's 1 times b squared minus 4ac? Well, that'd have to be b squared minus 4ac. What about that denominator? a times 4a. 4a squared. What are you going to do on both sides to get rid of this square? Take the square root. So we get x plus b over 2a equals, I think that numerator is pretty nasty looking, so we're going to leave it alone. Does anybody know the square root of 4a squared? 2a? You hear how it went up on the end there? That sounded like a question to me. Yes, 2a. Or not 2a. That is the question. Now, what's noticeably missing right here in front of the radical? We took the square root of both sides. Thank you, Miss Smothers. Plus or minus? Whenever we're in a solving situation, you take the square root, you got to have the plus and the minus. So what are we going to do to get this to move to the other side so we can get x by itself? Subtract. Boy, what does that look like? Really? Should look like a really familiar mess.
Oh, yeah.
Is this the quadratic formula? It is! Now, normally we quote it in one giant fraction, although hopefully you're smart enough to realize that what's so important about this thing right here? What is that? I would abbreviate it AOS. It's a line that cuts a parabola in half. Axis of symmetry. Thank you very much. Okay, axis of symmetry. That's what that thing is. And then, of course, you're adding and subtracting something, which is the distance to get to the x-intercepts. But, you know, that's something we will kind of review. Obviously, we tend to put it all in one giant fraction, but it doesn't need to be. It's got common denominators, so you can do that. The quadratic formula was born from the completing the square process. Now, I know that that's a nasty proof that you would never want to try to repeat, you know, especially in a testing situation. I'm not asking you to do that. What I am asking you to do is realize what happened back here. This fraction is very important to you. If you add that number to both sides of the equation and then do your factoring, life will be much easier for you. You will not make as many mistakes. If you reverse those two, which is what a lot of Algebra 2 teachers do, they like to pull out the factor and take the middle value, cut it in half, square it, and then kids get lost on what to add to the other side. It's up to you. If you want to do it the old-fashioned way, the way that the Algebra 2 teachers normally do it, you're more than welcome to. I think this tends to lend itself to a lot fewer problems. Now, we won't get to this portion of the 2-1 notes today, so I want you to hold on to this proof, you know, in your notes somewhere, because we will need it later on. We need to switch to the rest of the 2-1 notes, and eventually we're going to come back to completing the square, and we'll remember this b squared over 4a thing that we're going to do. What minute you can go to if you want to focus your attention on reviewing your polynomials. But, you know, we're going to go through these, you know, obviously the linear one we're going to go through pretty fast. Quadratic one, you know, we'll spend a little bit more time on just because you should be familiar with it since you had it in Algebra 1 and Algebra 2. But, you know, I understand we need to take a look at it more. And then other polynomial functions we need to do more with. And of course we'll get into rational functions and so forth. Okay, so let's look at this ugly definition of a polynomial function. So, first thing you need to see, it says that let n be a non-negative integer. Now, what is n? Now, n happens to be the highest exponent. And that has a cool name. We call it the degree of the polynomial. The degree of the polynomial. But it says it's got to be a non-negative integer. What does that mean? Can't be negative. Okay, so give me examples of non-negative integers. 1, yeah, that's an example. Okay. 1, 2, positive infinity. Sure. How about 5 over 2? Is 5 over 2 an example of an integer? Nope, that's 2.5. That is not in that group. We're missing one. 0 is a non-negative integer. So that is a possibility, yes. you can see that the exponents start decreasing. This is called standard form. So, in the standard form, wow, that's a bad looking number. We have decreasing exponents. You can tell because the next exponent after n is n minus 1. Of course, after that would be n minus 2, and n minus 3, and n minus 4, and n minus 5, all the way until we get to 2, 1. And then what is the exponent on the very end? Yeah, kind of. Noticeably missing at the end is x to the 0. Why? What is x to the 0 power? 1. Thank you very much. Nobody quotes x to the 0 because they would be made fun of at parties, possibly even kicked out. But x to the 0 is a 1. It is there at the end. We just don't generally write it. This right here would be called your constant term. It's something like 5 or 17 or negative 3. This term right here is not a constant term. What is it called? Something that has degree 1 has a cool name. You've studied it a lot in your life. I'll give you an example. 3x, 17x. Starts with an L, folks. Linear. Yes, it's the linear term. Nice. This is the linear term. Any thoughts on the next one? Whew, gonna be a long semester. Come on, the next one after that. Something with a square in it. Yeah, it's quadratic, right? It starts with a Q. I was going to say starts with a Q. I didn't know if that would be a big enough clue. Quadratic, right. And then we have other names like the next term would be cubic and then quartic, so on. Eventually we run out of cool names for those terms. And then we start calling them, 8th term, 9th term, 10th term, those kind of things. This term right here is fairly important to you. A sub n x to the n. Now we've already highlighted the fact that the degree, that's the n right there, that's the degree. But this thing right here, this thing's called the leading coefficient. I probably will abbreviate that like LC in the future, but that is the leading coefficient. This whole thing is called the leading term. Now, when we studied polynomials last year in Algebra 2, we learned a lot of information from that. We learned the end behavior from this term. I'm guessing that those rules are probably not in your brain at the moment, so we might want to figure out what that means. When the leading term was positive, what did that mean about the right end behavior? Is that okay to abbreviate? Or is that too much? Right Because you always need to find your right end behavior first. And when it was positive, what did you know about the polynomial? We would draw arrows. We would use parentheses like this, and we would draw arrows up and down. Is this ringing any bells? The right end behavior is what? Up or down? That's what I want to know. Is it up or is it down? It is up. Obviously, if it was negative, that would mean that the right end behavior would be down. And then we would look at the degree, okay? And the degree would be split into two parts. It's either odd or it's even. If it was odd, what did that tell you about the left end behavior? If it was odd, it would tell you that it was opposite. Look at that, ODD, OPP. It's like they go together, kind of. So we would say things like, if this was odd, then this would be opposite of the right. If it's even, it's the same as the right. It is entirely critical that you figure out what the right end behavior is first, so that we know whether it's opposite or same. Always look at the leading coefficient first. That determines whether the right end behavior is up or down. Okay? We'll get to an example here in a second. Okay? Okay? If we don't know what the right end behavior is referring to, remember on a graph, all in chapter, we would have all kinds of things like this, polynomials that we graphed last year. End behavior. Where is end behavior? If I asked you for the right end behavior of this graph, where am I looking? Am I looking to the far right or the far left for the right end behavior? Aren't I looking way out here? And if I'm looking way out there, what's going on with this graph that I've done in red? Isn't it definitely up on the right? That's kind of what we're asking, is what's going on with that end behavior. In fact, if we wrote it out in terms of limits, they're not going away, folks. For those of you who don't know how to write them yet, you need to learn, because they're not going away. So if I asked you for the limits as x goes to positive infinity of this particular graph, what would you say? You would say either positive infinity or does not exist, right? Because it just keeps getting higher and higher and higher. That's what we mean by right end behavior. What's going on way far on the right-hand side of the graph. So we'll practice a few of these here in a second, but I need to know which one of these are polynomial functions, and then we can do all the other cool stuff after that. So, look at letter A. Do we have non-negative integer exponents? Non-negative integer exponents. Well, is that a non-negative integer exponent? Yep. Is that a non-negative integer exponent? Yep. And then, of course, you got x to the 0. Is that a non-negative? Oh, yep, that's it. That's a good one right there. Because x to the 0 is 1. So it's that mysterious one kind of like that relative nobody talks about, but you know is still there. They never show up to the reunions, but you've heard about them. Never mind. Okay, so that's a definite yes right there. What about B? Does that qualify for a polynomial? I've got one person saying no. I've got two people saying no. Is that true? If you think that's a no, why? Is this a non-negative integer? So that's definitely a no. Correct. The exponent, according to the polynomial definition, the exponents have to be non-negative integers. Right there. All of those exponents have to be non-negative integers. Or based on a non-negative integer, I should say. And that definitely doesn't qualify. By the way, just a trip down Algebra 2 lane here. How would you write this? 6x to the negative fourth. What's another way to write this? Because we always asked you to write it with positive exponents. How would you write that? What'd you say? I heard it over here. Yes, I think I understand. What are we doing with that thing to change it from a negative 4 to a positive 4 exponent? Yeah, we want the reciprocal, so we'd end up with this. So that's another way to look at the same thing, and that's a showstopper when we're talking about polynomials. Okay, anytime you're dividing by a power, that's not a polynomial, folks. Okay, so that kind of goes along with that same idea of non-negative integer. I can to what? Just that? Okay. All right, so can you guys tell me 9x to the fourth plus 16x squared? What is the exponent that we could rewrite that radical to? The square root is what exponent? Not the second power. Try again. Come on, we talked about it last year. Square root is what for... Oh, I think I gave it away. What exponent? I need to know I need to know what exponent the square root is. Folks, like if we said the square root of 9, what's another way to say that's 9 to what power? The 1/2 power, man. Remember that? Fractional exponents? I know. We got to remember this stuff, folks. It's not like it disappears. It's a language that keeps building. Now, please, don't tell me that you can distribute that 1/2 power to everything in between, inside that parenthesis. Please don't tell me that, okay? What's stopping you from doing that? What is stopping you from distributing that 1/2 to every single exponent on the inside there, folks? Parentheses? Nope. Okay, you got about 20 seconds to talk to your neighbor and figure out what in the world inside that parenthesis is stopping you from distributing that 1/2 to everything on the inside. Talk to your neighbors.
Sure. I'd like to hear about them and their thoughts and say, what's stopping us from distributing that 1/2 exponent through there? Because I know you all want to, but it's illegal.
By the way, a lot of you did really well on that retake and improved your grade quite a bit. Nice job.
A lot of people did. Sure. Stop by anytime. Here, I'll put some evening classes on there too. Today wouldn't be the best, but I could. Definitely tomorrow would be fine. Wednesday, sure. Friday, not my favorite, but okay. You can stop by and talk to me about that. I'd be happy to go over it with you. I'm not sure I'm going to use class time for it, but yep, you can go over it with me. Okay, what's stopping us? Addition. Addition is stopping you from doing that because you guys want to distribute that 1/2 all the way through there, which means that I know what you're doing. You're going back to This, in your brain, you're going back to a multiplication property, and that's legal right there. It's legal to distribute that 1/2 to every exponent on the inside when it's multiplication. Not true for addition. So, does this qualify as a fractional exponent? Or a polynomials, I guess I should ask. Are the exponents non-negative integers? So that's definitely a big no. We're not talking about a polynomial there. It doesn't fit the definition. What about the last one, D? Does it fit the definition? Look at the exponents of every term and tell me whether they're non-negative. That's true, they are. That does qualify. That's a big yes. Now, for the ones that are polynomials, now I do see that they're trying to trick me here, folks. They did not write it in standard form, so, you know, we're not going to fall for that trick. They want to know about the degree. Okay, so let's go back to letter A. Oops, that's not. Tell me what the degree is. That's a third degree. Thank you very much. You saw that right there. What's the leading coefficient? Leading coefficient. 4. Nicely done. Now let's think about the end behavior of this one without actually graphing it. We have a positive leading coefficient. What does that mean about the right end behavior? Going up. We have an odd degree. What does that mean about the left? Opposite of the right. Okay, let's look at D. And then, yes, I can zoom out. What's the degree? That's a 4th degree, right? What's the leading coefficient? -2. Okay, now let's talk end behavior. Since the leading coefficient is negative, what do you know about the right end behavior? It is down. Since the degree is even, what do you know about the left? It's the same as the right. So even without graphing this thing, I can tell you that much about it. That would be great. It would be great to just ask you a limit question as x approaches negative infinity. And give you the choices of positive infinity or negative infinity. It'd be a pretty simple multiple choice question. You would either know your end behavior or you wouldn't. Okay. Now, in example 2 here, this should be a pretty simple, straightforward example. What? Sure. All right. Find an equation of a linear function. You've done this for a long time, so this should be pretty easy. What did they give you? What is this thing you're staring at right here? Okay, but what is it? What did they just hand you? They handed you an x and a y. They gave you a coordinate. What is that coordinate? The x value is what? Negative 1. The y value is 2. Remember, f of x is a fancy way to say y. Which is why I have that sign outside my door. Some people ask f of x. What's the other coordinate? Every time you want to find the equation of a linear function given 2 points, what do you need to figure out? Oh my goodness, this is killing me. Come on, faster. You got 2 points. Find the line that goes through them. What do you need to figure out? The slope. Thank you very much. 2 minus negative 2 equals something, and negative 1 minus 3. So what's 2 minus negative 2? 4. And negative 1 minus 3 is negative 4. Therefore, our slope is negative 1. Thank you very much. So, pick your favorite point. Which point would you like to pick? Ms. Hensley, what do you got? Which point would you like? We got to use a point. All right, she picks that one. All right, so y minus 2 equals negative 1 times x plus 1. Okay, get y by itself just for kicks and giggles. A little bit of algebra practice. Should take you about 10 seconds. And voila, hopefully you ended up with that. We just took the point that she chose. She chose negative 1, 2. Use the good old point slope version of the equation of a line. We plugged in our x1 and our y1. It's just kind of like, oh my goodness, it's like fireproof form of a linear function. Look at that. That's your y minus k and your x plus h. Or x minus h. Whoa. I know, man. Where have you heard this phrase, average rate of change? What is it? Starts with an S. Slope. School. You're about to be. Okay, now. So that is a slope, right? Average rate of change. Okay, and what is this? What is f of b minus f of a? What do we call this thing? Don't we call it the rise? Difference in the y values? You've never heard the rise over the run? Isn't that slope? You know why I spell rise like that? Because I have pre-calc kids that tell me that the x's should go in the numerator. And it kills me. Breaks my heart. Okay? And we shall continue this battle on a different day. 1 through 12 is what you need to be working on and finishing tonight. I'll look at those tomorrow. 1 through 12.